Okay, folks, we want to talk today about the first part of the next lecture, which is the lecture number 17, about the difference of means and also about the difference of proportions. This is the first part in which we are going to be doing the estimates, and then in the second part we're going to be talking about the tests. Uh, what is this about? Well, when we are estimating mean of population, we have two types of estimates we usually did. In the past, one was the z-estimate of the mean, and another one was a t-estimate of the mean. So we use a confidence interval for that particular purpose, right? And that, for example, in the case of a z-estimate for the mean, we would use the following confidence interval. We have the point estimate, which is the mean of the sample, and then we get the uh, margin of error, which is when you multiply the critical value with the following standard error, right? So we have this for an estimate of the mean. In this particular estimate, we said you need to know the population standard deviation of the variable, whatever you were estimating mean of, and obviously you would know the sample size, and the critical value depends on the particular level of confidence you want. When you're doing a t-estimate, then you would do the t-estimate of the mean would have a similar formula, but of course the critical value would be the t value, the student t random variable, and the estimate itself would have the sample standard deviation, sample variance instead of the population variance, right? By the way, if you take the radical here on the top, you can get rid of the square, and then you have just radical on the bottom. So that's another way of writing it. So for example, which you often seen in formula is something like that, right? Now, I will not use that. I will use the original what I wrote because I want to show you something. Okay. So those are the two types of estimates we do for the two different confidence intervals which we do for the estimate of the population mean. We also estimate population proportion, and for that particular interval we use the proportion of the sample, and that is the only kind of estimate we do is the z-estimate, because of course for the t-estimate you need to have a variable that is distributed normally, and the proportion is out of the Pauling, out of Bernoulli random variable, Bellomi random variable, which is definitely not normal. And then we also have the standard error, and that would be something like this. And of course, because you estimate population proportion, you definitely would not know the population proportion which you're trying to estimate. So we replace that with what we get out of the sample. So that's the estimate of population proportion. These are the two estimates of the population mean when you're dealing with the single mean of a single variable. Okay, now what if you're doing that for two different variables in which you would be interested in finding out the difference between the two different variables? So for example, if you're estimating proportion, you could estimate the proportion of the from a poll male voters that would vote for a particular political candidate, and the proportion of female voters that would vote for political candidates. And then you would like to know the difference of these two. Or any other situation in which you find yourself and you're you're having one population that falls one particular way, you have another population that falls another particular way. You're not really interested in the means themselves, but you're interested in the difference of the two means. Okay, so that would be the situation in which we would be using the estimate of a difference of means as opposed to estimate of a single mean. Now, the question is, how do I modify this formula so that I would have the difference of means of estimate? So this is a z estimate of a single population mean. This is a t estimate of a single population mean. This is a z estimate of a single population proportion. But what if I have a 2? What would happen? Okay, so the idea will be, obviously, I will have the point estimate. So if I have a 2 means, and I have in the game I would have 2 variables. One would be called an x, and I guess another one I would call y. So I'm interested in the difference of mean of x and y. These two. So I'd have something for an x, the population mean for an x, and some population mean for a y, but I would be interested in finding out what is the difference of the two means. What would be this particular number? Of course, there is a particular number because there is a population of x values and population of y values, and there is an average of those x values, which is a population mean, and average of those y values, which is a population mean for y. And now there must be a difference, right? So that's a single number. So if you want to estimate that number, what would I have to do? Well, I guess I would get something from the sample for an x, I would get something from a sample for a y, so my point estimate would be simply the difference of the two means I get in the samples. So I'm getting the sample mean of x, sample mean of y, and when I subtract those two, I guess that would be the estimate of the difference of two means in the population. So I'm having I want to estimate this, but I'm going to, of course, use this for my point estimate. So this is what I got from the sample. This is in the population what I don't know, so I'm estimating. Okay, in the z estimate, of course, I'll keep the critical value, z. Here I have the nth of the variance for an x originally I have. But now I have two variables. So what this is, we know that from a story about central limit theorem, this would be, if it's just one variable, right? This would be the variance of the x bar. Okay? So I need to now replace this variance of the x bar with the variance of this guy. Now I don't have any more. Originally I did have, when I was talking about a single mean, I have the sample mean here, and this is the variance of this guy. This is a variable, right? Depends on a sample. In one sample one thing, another sample another thing, and so on. It has its own variance. The central limit theorem says this is the variance of this guy. Okay, but now you have different variable, this one here. So I need to replace the variance of this guy with the variance of this, the variance of the difference of the two sample means. So what am I going to use here? What am I going to write here? What is the variance of this thing? Okay, let me think about it. Let's say we have shoe sizes. female shoe sizes and male shoe sizes. And I'm not going to use the shoe size, which will be actually something else, but I'm going to use the length of shoe in inches. So supposedly you have the shoe sizes of a bunch of males. Something like that. So I have 1, 2, 3, 4, 5, 6 males, and those are their shoe sizes. Some guy has 10 inches, 11 inches, 11 and a half inches, 12 inches, 13 inches, 13 inches. Maybe I made it too big, but it doesn't make any difference really. Okay, now, female shoe sizes. So I have a 1, 2, doesn't have to be the same number, so let's have one more. 3 ladies with the same shoe size, 9. So I get 1, 2, 3, 4, 5, 6, 7 ladies, and they have these shoe sizes. Okay, now, what is the range of these male shoe sizes? Range is obviously 3, right? The bigger shoe size, the smaller shoe size. In terms of a female shoe sizes, the range is 2. As you probably know from the statistics 1, range is the simplest possible measure you can have about the variation, right? So I have the first sample has range 3, the second sample has range 2. Now, let's take all of the differences I could have. Differences. Right, so here is the difference I could have, it's 3. This difference is 4. And on you go. In either case, the smallest difference I would have would be, the smallest difference would be this and this, which would be 1. Right? The smallest shoe size for a male, the biggest shoe size for a female, and that would be the smallest difference that I would have. The biggest difference I would have would be from the shoe size, so there are a bunch of other differences in between, but then I had the biggest difference I would have from the biggest shoe size for a male and the smallest shoe size for a female, which would be 6, right? So again, look at all of the possible differences you can find out. So male shoe size, female shoe size, 3. Male shoe size, female shoe size, the difference is 5 here. And on you go. You can find all of the possible differences you can see from one male and one female. But the biggest one you would find would be 6, and the smallest one you would find would be 1. Okay? So, all of those differences, I didn't write them all, because you have to actually write 30 of them. You have a 42 of them. You have a 6 male shoe sizes, 7 female shoe sizes. You pair them all, you'll find a 42 pairs, and the smallest difference you'd find would be 1. The biggest difference you would find would be 6. So the range of differences is from 1 to 6, which is 5. Okay? That gives you an idea that the range of differences is equal to the sum of the individual ranges. Okay? This thing here is the difference of two means, which is also a mean of the differences. So the variation of the differences will be the sum of their individual variations. So variation of this and variation of this. So now I have it. So again, this is a variance of this guy. This is a variance of this guy. When you're looking for the difference and all the possible differences you can find, this would be the mean of those differences. And the variation of those differences, just like for the range, of course, variance and the range are not the same thing. So I'm not arguing that. I'm arguing that when you're looking for the range of differences, you will find out the variation of that range of differences. The range of those differences will be the sum of the individual ranges. The same thing for variance. The variance of differences between two variables will be the sum of their original variances. Now, what I'm saying here is a fact of a probability, which you would need to study to figure it out. It's not a proof. I didn't prove anything. I just give you an argument for that. But that's what we get for the formula. So again, that is a fact that you can prove, and you can show that if you study a little more serious probability. We're not going to do that, but we will use it. So again, wow, what happened? Actually, I have a formula to estimate the population, the difference of two population means. So again, I was trying, in this particular case, I was trying to estimate what is the difference of two populations. Population means, I should say. Okay, this is my estimate. What's gonna change in the t-estimate? Nothing special. I'm just going to have the same point estimate. And I'm going to have here two sample standard deviation, one for dx and one for dy. Okay, now I didn't say that yet, but I should say that n1 and n2 are respective to what the sample sizes are. So the sample sizes could be different. They don't have to be the same. So you might have a sample size for x's to like I have for those males, 6, and I had a sample size for female shoes, I had 7 of them. So these two numbers could be different. So the first number refers to how many things you have in the sample for an X, and the second one refers to how many things you have in the sample for a Y. So this is a Z estimate for a difference of two means. This is a T estimate for a difference of two means. Now you could ask a question, when do I use one, when do I use another? The rule is very simple. You would use the t-estimate just like in the past. When you have a situation that both of the variables x and y are normal, you need to have that, and the one of the variances will be unknown. One of the population standard deviation or population variance, one of the population standard deviation would be unknown. So you either would not know this guy or you would not know this guy. When you have that situation, you will use t-estimate. Again, you gotta remember that. You would use a t-estimate when you don't know both of these guys. That's all there is to it. And obviously, when you have the x and y both normal, right? So you might ask this question, when I don't know both of those guys? Well, you don't know them when you don't know one of them. If you don't know this guy, then you don't know both. If you don't know this guy, then you don't know both. If you don't know this one and this one, then you don't know both. Right? You need to think here, right? So if you know them both, obviously you're going to use the Z estimate. So again, if you don't know one of them, that means you don't know both of them. And if the x and y are both distributed normally, then you have a t-estimate. In the other cases, you would have z-estimate, assuming you can make an estimate. Now we said that in the past, and it applies here, if the sample is too small, and the variable is not distributed normally, then you don't have enough information to do any estimate. So if the sample for an X is too small, or the sample for a Y is too small, and you cannot say X is distributed normally or Y is distributed normally, then you cannot use any estimate. Okay, now what will happen in the proportion business? In the proportion story, you would have a proportion for the X, proportion for the Y, so you have two variables, and the estimate for the difference of two means would be like that. You don't really have a two means, you have you're estimating, in this particular case you are estimating the difference of two proportions. Proportion in the population for X, proportion in the population for Y. Okay? And here you would also replace this is the variance for, if you have an X here, the variance for an X, but then you have variance for both X and Y, so you're just going to sum them. So the formula changes into the following one. And again, N1 refers to the size of the sample you have for the X's, and N2 refers to the size of the sample you have for Y. So again, this is a Z estimate for the difference of two proportions. There is no T estimate there, it's only Z estimate. This is a Z estimate for the difference of two population means. This is a T estimate for the difference of two population means. And again, you use T estimate when both variables, X and Y, are distributed normally, number one, and number two, you don't know one of these guys, or both of them. Which means you don't have full information to put in this formula. And if something is missing, then you're going to use this. But you do need to have X and Y distributed normally. If you don't have that, you have nothing to work with. Okay? So let me give you a couple of examples. This is all theories so far, right? I give you lots of theories, and you might get confused. What is this guy talking about? I don't see any thing here. All right. So let me give you an example. The first one says, this is example number 1 from the lecture on the difference of mean, lecture number 17 on the Blackboard. You can find it. So I'm going to read it for you. It says, of two similar groups of patients, one group is called A, another group we're going to call B. In the first group we have 50 patients. In the second group we have 100 patients. Okay? The first group was given a new type of a sleeping pill. So these 50 people receive a sleeping pill, the new type of a sleeping pill, and in that group, when their length of the sleep was measured, we got 7.82 hours. So on average, they were sleeping, 50 of them. After taking that pill, on average, they were sleeping 7.82 hours. Which means I have, this is an example, number 1, again in the lecture, I have that the first group was sleeping on average this many hours. Okay? The second group was getting there was a control group, so they were getting the old sleeping pill. So there is a new sleeping pill and the old sleeping pill. The second group of 100 of them were getting the old sleeping pill. The old sleeping pill was probably something that this company was selling before. They decided to make a new one. So in this second group, they were sleeping on average 6.75 hours. the units are in hours. Sleeping time. So there were 100 of them. They were taking, all of them were taking this old type of a sleeping pill, and on average, they were sleeping 6.75. But of course, not everybody was sleeping that amount of hours, so there were variations. So we got also that in the first group, the standard population standard deviation was 0.24. In the second group, we have a population standard deviation of 0.3 hours. So in the first group, there was a standard deviation of the population about a quarter of an hour, right? So that would be like 15 minutes. So it's actually a little less than a quarter. And the second group was a little bigger variation, 0.3. Okay? So now, I want to know what is the difference between the sleeping time from the old sleeping pill to the new sleeping pill. That will also give me some idea about an improvement, right? I guess you want to sleep longer. When you take a sleeping pill, the idea is you want to sleep longer because that would be the reason for taking a sleeping pill. Okay? Now, you might want to ask me a question, which would be a good question. How do I know population standard deviation for these two? Let's just assume we know that, right? This is that story. If you don't know that, then you're going to have to probably use a sample standard deviation, which would be okay, because we have two large samples. 50 and 100 are large samples. So we said in the past, when you have a large sample, you can replace the population standard deviation with the sample standard deviation. Okay? So again, if you don't know the population standard deviation, and if you know only sample standard deviation, if the sample is large, you could make that leap in approximation. You can replace it with the sample standard deviation. But I do have the population standard deviation. Okay? So here is my estimate. Again, I'm going to use the z-estimate because I know the population standard deviation. Okay, so the z-estimate would say you have x bar minus y bar, which is going to be 7.82 minus 6.75, give or take. Oh, now what confidence I want. So in this particular example, we were looking for something really very close to a certain 99%. Let's use 99% confidence, so we can, get this with a 99% confidence estimate. That would be 99% confidence interval. So I have that. You remember that story for the critical value for 99% confidence was 2.576, right? I hope you remember that. If not, take a look at the t-tables. That's on the bottom of the t-tables. And finally, I have the radical here. So in the radical, I need to put the 0.24. I need to square that. And I need to divide with how many things I have in that sample. In the first sample, the first group, I have 50 people. And in the second group, I have 0.3 to square. Squaring that. And I'm going to divide it with 100 because that's how many people I have in the second group. So this is my 99% confidence interval. I'm estimating the difference of the mean times for those two sleeping pills. How much better is that new sleeping pill? So I'm using the new sleeping pill, the average here, the all sleeping pill, the average here. Right? These are the sample averages, but I'm estimating population average. So I'm getting, after I calculated, I got this one to be 1.07 hours. Everything is in hours, give or take, and that thing here into square this, I need to divide, square this, divide, add it, take a radical, multiply 2.576, and you would eventually get 0.117. It's pretty good estimate. So this is 12% of an hour. How much that would be? I don't know. 12% of an hour. That's the 10% of an hour is what, 6 minutes, right? 12%, maybe 1 minute more, so like 7 minutes. So a little more than an hour, give or take 7 minutes. You really need to turn this into minutes if you want to know exactly what it is. But it's quite clear here that we have a big difference between the new sleeping pill and old sleeping pill. My estimate is that it ranges somewhere between, if you subtract this number, you're going to have the lower end. It's going to be 0.953, and if you add, it's going to be 1.187. So that would be the interval in terms of hours. So we have quite a bit of a difference, right? So I was just figuring out how much better is the new sleeping pill. Okay? So I used the estimate, Z estimate for this particular situation in which I have the access to be a sleeping time with the new sleeping pill and sleeping time with the old sleeping pill. I need to say another thing about it. This whole story we're having today is applicable on the samples that are independent. When the samples are dependent, then the story is completely different. And we're going to have to talk about it separately. If we do, we might have enough time to do it. So again, the group of patients in the first group, 50 of them, and the group of patients in the second group, 100 of them, should not be related in any way. Okay? You can ask question, how can you make that related? Well, I can make it easily related. I can have the same group of people, give them the new sleeping pill, I measure that, I get the average, and then, the next week I give them the old sleeping pill, and then I measure that and I get the average. Now that would be dependent sample because they will be the same people in two samples, right? So we have to be careful. Again, the whole story I have today here, everything I'm going to be doing today is about the two independent samples. So the populations X's and the population in Y's cannot be related, right? That's important to know, because otherwise I have a different story for you, okay? Let's talk about the estimate of the proportion, difference of two proportions. Right. There is one marketing example. So this is again example number 2 in the lecture. So you need to read that, but I will read it for you. So what the story is, it says, in a random sample of 400 adults and 600 teenagers. Notice, I have a big sample sizes, which is always necessary whenever you're doing estimate of proportion. Z estimate of proportion requires you to have large samples. This is the old story and the new story, the same. If you're estimating proportion, you need to have large sample. So I have 400 adults and 600 teenagers, two different groups. And obviously they're not related, right? And they were watching certain TV program. Okay? In that TV program there was some attraction for kids and not so much for adults. So only 100 out of 400 adults said they liked that program. On the other hand, out of the 600 teenagers, 300 said they like it. Okay? So you can see there is some difference, obviously, right? So the adults they were not that much enamored in that program, but the teenagers were having a much better time with it. Okay, so the question is, can you estimate the difference of the proportion of adults and proportion of the teenagers that would like that program in the population? You have a sample of 400, sample of 600. Can you tell me what's the difference in the population? Difference of proportion is very often estimated, right? Sometimes you estimate, what is the difference of male and female voters voting for some political candidate, things like that. I'm not doing that here. I'm doing what is the interest in adults and interest in teenagers for particular TV programs. So, okay. So I had the proportion of teenagers that like that program. So we're gonna call that PX. You can always take the first number to be bigger to avoid to get negative numbers. So if the proportion of teenagers is bigger, use that as an X. X teenagers. Right? So I get that, what did I say? 300 out of 600 like that. So that's 50%. Okay? Proportion of adults that liked that program was much smaller. So proportion of adults was 100 out of 400. So that's a quarter. So proportion of teenagers that like that program in my sample is 50%, 300 out of 600. The proportion of adults that like that program was 100 out of 400, which is 1/4. So let me just write also that I have that N1. So this is the group of teenagers. I have 600 of them, and I have a group of adults, N2, and that was 400. Okay. To identify what my sample is. Okay, now I'd like to know what is the difference in the population. So the difference in the population will be by the Z estimate. So this is the formula for the difference in the population. So now just fill it up. What do we have here is 0.50 minus 0.25, give or take. So we have this margin of error, right? You remember the story goes on the same as before. Point estimate, margin of error, standard error, critical value. Right? The same thing here. Point estimate, margin of error, standard error, critical value. Point estimate, margin of error, or the maximum error estimate, sometimes called that way. Critical value, standard error. So that's the same story as before. So the radical is the standard error, and multiply with the critical value, you get a margin of error, or we call that maximum error estimate. And the thing before that, plus or minus, that's your actual point estimate. So I have the same thing here. My point estimate is quarter. This is very easy to see. This is going to be quarter, right? But the rest of them I need to do a calculation. I need to have this guy. We're gonna use this when we don't have anything better. We just use 95% confidence, right? So that's gonna be 1.960. 90% confidence. So the critical value to remember is 1.960 multiplied with. Now you have to write that thing down. So we have a PX, which is 0.5. QX is a complementary value, which is also 0.5, 50-50, right? Divided with N1, which is 600. And the more we have to do, PY 0.25. The complementary to 25% is 75%, so that's a Q, Y, and the N2 is 400. So once again, you have the 95% confidence interval, straight out of that formula over there, nothing special. The only thing you need to is to calculate. The first part is easy. This is quarter, or 0.25. This you're gonna have to work it out, right? So you're gonna have to multiply this 2, divide with 600, multiply that, divide with 400, add it up, take a radical, multiply 1.960. But this is what I got. I got 0.25, and there I got, give or take, 0.06. Alright, so that's my confidence interval, where I can say that this is the proportion of teenagers that like this program more than the adults. I'm 95% confidence. It's anywhere between 19%, so when you subtract you get 19%, so you get 25%, give or take 6%. When you subtract you get 19%, and when you add you got 31%. So you can also say that, which is very often how it's done in the textbook, that your confidence interval is from 0.19 up to 0.31. It's a different way to write the same conclusion, but we can say with 95% confidence, at least 19% of teenagers will like this program better than the adults. It might be all the way up to 31% of teenagers would like that program more than the adults would. Okay, I just concluded that out of the calculating the formula over there that I use, right? Okay, how about 1t estimate? Okay, so example number 3, also from the lecture in the on the blackboard, lecture number 17. So you're gonna read that example if you don't follow what my story is here. We have a story about a biologist, and this biologist is working on some on 2 sets of a rare bird, might be the same species. So I could have a Charles Darwin story for you here. One of the sets of birds were on the continent, and the other set of the same species was on an island. And we get the guys that were on the island, they had a little bigger wingspan because they had to fly more. So that over time they develop a little bigger wingspans. It's kind of interesting situation. You have the same species. The ones that were on the island, they have a little bigger wingspan than the ones that are on the continent. Okay, now the question is, what is the difference? Right? So the story says that he found 19 of them on the island, 19 birds with a mean wingspan of 8.8 inches and the sample standard deviation of 2.3 inches. So the mean wingspan of the first group, the birds, you can call it the birds on island. I'm not making it up, the birds on island or whatever. They have 8.8 inches mean wingspan. You know what a wingspan is, I'm assuming, right? And there was a standard deviation, of course. Not every bird had the same wingspan, so there was standard deviation. Standard deviation in the sample was 2.3 inches. Okay? So I don't know the population standard deviation, right? You can see that. And the number of birds in that group was 19. Okay, so the mean wingspan of the birds in the first group was 8.8 inches, The sample standard deviation was 2.3 inches, and the number of birds in that group was 19. In the second group, that's continental group, you can call it, we have 15 birds. Their mean wingspan was slightly smaller. It was 7.5 inches. And they also have standard deviation again from bird to bird. There was a difference in wingspan, so there was a variation. And the standard deviation that measures the variation was 1.9 inches. And out of that story, we know that this is a sample standard deviation, because the way the story goes, it doesn't tell you anything about the population standard deviation. It says, in this group we have mean wingspan 8.8 and standard deviation 2.3. In the second group we have mean wingspan 7.5 and standard deviation 1.9. I mean, you're not told anything better, you can guess this must be a sample standard deviation, right? Okay, so what do we have? Well, we definitely cannot use this formula. Why not? Well, we don't know the population standard deviation, no, only sample standard deviation. You can say, well, you can replace that if you have a big sample, but this is not a big sample, so you cannot use it. So, this formula is excluded. This is not a story about the proportion, apparently. So, we are left with the question, can we possibly use this one here? And the answer is yes. Why? Because the wingspan of a bird, or any species, from a bird to a bird, that's a measurement of a living being. And we said it in the past, measurement of living beings almost always are normal, especially the wingspan of wild birds. They're normally distributed. So that's a great thing. So you have a normal distribution for an X. You have a normal distribution, that's continental, island birds. You have a normal distribution for Y. Those are the continental birds. And you also have unknown population standard deviation. Obviously, both of the population standard deviation are unknown. So you have all the ingredients for the T estimate. Okay, so now you're going to use this formula. Very simple. 8.8 minus 7.5. This is your point estimate. So the point estimate is least the difference of, not the least, but the difference is 1.3 inches. The island birds have 1.3 inches longer wingspan. But that, of course, is a point estimate, so you need to have a give or take. Alright? Now that give or take will have a critical value. I'm going to write it later. Well, let me see what is in the radical. In the radical is very simple. So I have 2.3. I need to square that. I need to divide it with 19. And I have the second fraction. SY 1.9. I need to square that, and I need to divide it with 15. So that's going to be easy to calculate. Of course, with a calculator, right? No, you could probably do it without calculator as well. Now, critical value, for T critical value goes here. Okay, now we have a little story here. In the first group, you have 19 birds. The degrees of freedom in the first sample is 18. One less the size of the sample. Size of the sample is 19. In the second group, you have 15 birds, which means the degrees of freedom in your sample is 14. So we have 18 in the first group and 14 in the second group. Now the question is, what is our degrees of freedom that we're going to use for the critical value here? Because this guy is associated with degrees of freedom. It's not the same. Depends on what degrees of freedom is. If degrees of freedom changes, then this value changes, regardless of whether you fixed your confidence. Now, this particular confidence, I'm going to use 90%. Okay? So 90% confidence, but it depends on the degrees of freedom too. Okay? There are ways to interpolate that. We are not going to do that. But that is something that your calculator would be able to do. So we're going to use a more conservative, 14. So you have a choice to either use 18 or 14 or something else. We're going to use the most conservative. The least amount of freedom is going to be 14. So we're going to use 14 degrees of freedom. This is always going to be our approach. This is also the textbook approach. You're not going to have a problem with the homework. So again, if you are going to use a critical value here, the critical value will be depending, of course, on the confidence. We're going to use 90% confidence, but also depends on degrees of freedom. So you're going to be looking at degrees of freedom here, which is 18, degrees of freedom here, which is 14, and you're going to use the smaller one. You got to remember that. So now I'm using 14 degrees of freedom, 90% confidence. I'm assuming you know how to use t-tables, right? Because you have done this in the past. So you need to open the t-tables. In the t-tables, you're going to look at the top, very top. It says 90% confidence, and you're going to find the 14 degrees of freedom in that column. 14 degrees of freedom, 90% confidence. Number that I'm looking for is 1.791. 61, excuse me. So that's the critical value. Again, this guy is associated with the confidence. The confidence we are using is 90% confidence. It is also associated with degrees of freedom that we are using the smaller one of these two. 18, 14, 14. Okay? The rest is peanuts. So the rest of the story goes on here. I need to calculate this, and I'm coming up with, this is easy, 1.3 give or take, and the rest of that is 1.269. That's my estimate. If I want to have an interval, which I probably want, then I'm going to do the interval thing. I'm going to be subtracting for the lower edge of the interval, lower bound. And I'm getting lower bound to be 0. When you subtract 1.3 minus 1.269, so I'm getting 0.031. Like a third of an inch. All the way up to, perhaps the difference is, when you add this, 2.569 inches. The whole interval is from positive 0.031 to 2.569. So you can actually claim here with a 90% of confidence that the island birds have a bigger wingspan, because our estimate goes somewhere between 0.031 all the way up to 2.569. Okay? So the difference of the wingspan of an island and a continental bird here is somewhere between this many inches all the way up to this many inches. It could be as little as a third of an inch, or excuse me, a 30th of an inch, not a third. Third would be if I have 3 here, right? All the way up to 2.5 inches, 2.569 inches. Okay, that's our estimate. Okay, so now I guess you see those 3 examples. I use that for any one of those estimates. So let me repeat this one more time, what we have for the formulas. So you are estimating the difference of 2 means. So you have a 2 population, X population and a Y population. You will have a mean in the X population, you will have the mean in the Y population. You're interested in finding out the difference. You could also have that for the proportions. So you have a proportion in the X population, proportion in the Y population. And you'll be looking for the difference of the proportion in one population to another population. What's the difference, right? Okay? So that's what we are estimating. We are estimating the difference of population mean or the difference of population proportions. Difference of two population means or difference of two population proportions. Those are actual numbers, they're parameters, we don't know what they are because they're in the population. So we are trying to estimate it. In case of an estimate, if you are doing a z-interval estimate, you will have the point estimate, which is going to be anything you get out of the sample for the first population minus whatever you got from the sample, the mean of the sample in the second population, and then you're going to have margin of error. And margin of error for the z-interval, of course, is going to have the z-critical value, which is going to be relative to whatever confidence you want it, multiply with the variation, the variance of this guy, which we were intuitively from the beginning concluded it is this guy. So that's the variance of this thing here. So again, there's no minus here, it's plus. The ranges of differences are adding, not subtracting, even to the difference. Okay, if you're doing a t-interval estimate, you will need to have both x and y distributed normally, and one of these or both of them unknown. If you don't know one of them, then you don't have enough information to put it here. Okay, because you're missing something. If you do know both of them, then by all means use the interval. Okay, but with the t-interval we have, again, the point estimate is the same. The difference of two sample means, give or take. Now I have a critical t-value. The critical t-value, and here you have the radical, in which you now have a sample variance. Divided with whatever you have in that sample, sample variance, whatever you have in this second sample. Okay? And this t-value will be smaller relative to smaller of and 1 minus 1 and 2 minus 1 degrees of freedom. So degrees of freedom is smaller of degrees of freedom in this sample and degrees of freedom of this sample. So you're going to have two different samples, degrees of freedom in first sample, degrees of freedom in second sample. The smaller one you will take for degrees of freedom for this value. Of course, this value, just like this value here, also depends on the confidence. So you're going to have particular confidence in the game. So that's for the estimating of a mean. Difference of two means, excuse me. To estimate the difference of two proportion, you only have a z-interval. And so I'm not going to write z-interval because that's the only thing you can use. And it's going to be, again, the point estimate, whatever you got out of these samples. So the proportion of one sample minus proportion of another sample, give or take, z critical value, and now you have the variance of this guy, which is going to be the following. But of course, since you don't know the population proportion of x and y, you're trying to estimate the difference, so you would not know what they are. You're gonna be able to replace that with the sample values if you have a large sample, and you have to have a large sample whenever you're estimating proportion. So that's your formula for the confidence interval, z confidence interval for difference to proportion. Okay, you gotta also remember the following. You will always use the x to be bigger values, the y to be smaller values, the x to be bigger values, the y to be smaller values. The same thing here. You don't have to use that, that's not needed. But if you don't use it that way, then you are going to end up with negative numbers, right? So if I use that story about birds, if I use x to be the wingspan for the smaller wingspan of the birds that are on the continent, and then I use this one for the wingspan of the bigger birds and the birds that are on the island, I would end up with this being negative, which you can use. But I know lots of people get confused with that when they get negative. What does that mean? Well, that means you just have the second group had a bigger wingspan than the first one, so that's why you got negative. So to avoid that problem, you can just always use x to be relative to bigger numbers and y relative to smaller numbers. So you're going to avoid the problem of getting your point estimate to be negative. Now the edges of interval, that's a different story. They could turn out to be, one of them could turn out to be negative anyway. Right? So again, this refers to the story when the two samples are independent. They could not be dependent. So you could not have a relation between the items in the first sample and the items in the second sample. Because if you have that, then you have the samples that are dependent. Right? If you don't have that, if the sample points are chosen at random birds on the island, random birds on the continent, they are not related, they are not brothers and sisters, then you have an independent sample. Okay, like those people that were taking pills, the first group of people, the second group of people, unrelated to the first group, independent sample. If you would have the same people doing both experiments with the first pill and the second pill, then you have dependent samples. So that's the story is different. It's not the story that we had today. Okay, now next time we meet, we're going to be talking about how do you test the difference of two means. Because there could be a claim that there is something about the difference of two means is something. It's might be bigger or smaller or equal to something. So we're going to talk about it next time. Hypothesis testing on difference of means claims. You know, in the past we have a hypothesis testing about claims about one mean and claims about one proportion. Now we're going to have a hypothesis testing of claims about the difference of means. Right? So we'll talk about it next time. I hope you can remember this. This is the part of this story, the part of the homework on the difference of means and difference of proportion is the homework number 12. But there is also hypothesis testing there. So maybe you might want to wait till we meet next time when we do the second part of this lecture. And we're going to complete then, we're going to be talking about hypothesis testing of difference of means and difference of proportion. Right? Okay, I'm going to end this story today, and again, the next time we're going to complete the lecture number 17. This is just the first half of it. See you the next time.